So we are meeting today after a long break. So I'll briefly remind you what is going on. We are studying the following problems. We start with quantum field theory, probably with brains, on Rd minus 1 times S1. And our goal is to see in the most elementary way what it would be as quantum field theory tilde, also with brains, on R d minus 1. It's called compactification. Coordinate here would be called xd. So what we have seen, suppose we have the p brane in QFT. With tension TP. After compactification, we get P brane with tension Tp plus a tower of P minus 1 brane with tensions, I call it rho Cp K. So sorry, it's rho, it's not P. Okay, I will call it R. How this tower appears. So the brain wraps K times and gives P minus 1 brane. The simplest example is if you have a zero brane that is like a particle, then this particle makes a loop and we have a point. Now what is the reason of this formula? The reason of this formula is that the action of P minus 1, I'll call it K brane, is given by the area So this R is circumference of the circle. So in the simplest case of a particle that gives a point, it's like this. So the length is k times r. In the more sophisticated case, where we have a string, picture is like this. This is the area. So this is the trajectory in RD minus 1. And it is clear that the area is, so for the case k equals to 1, the area is of course length times r. So it's the simplest case. It's an explanation of such a formula.
Excuse me, area of what?
Sorry?
The area of what?
So this is the area of the string trajectory in the space-time. String is a circle. This circle goes like this. And here we have an area. And this is a cylinder. And it's clear that the area is L times R. And for the action, I multiply it by what most people are calling P1.
Can you show me when k is 2, what happens?
When k is 2, what happens? The easiest way to show it so my hand is the space-time. So this is k equals.
Yeah, so
So area is multiplied by the covering number. So like here, if I write many times, the length of the wire is pretty big. And I will have a massive part.
and this L, you call it the length of string. L.
So this L is the length of the trajectory in RD minus 1. This R is circumference. But I'd like to see this wrapped string as a particle. So it is an example. In this elementary theory of brains and quantum field theories, we had a concept of charge. Charge of P brain. So before we speak about charge of P brain, we imagine that we have a field B. That is P plus 1, 4. And we say that P brain is charged if there is such term in the action. So I take this B and I integrate over the trajectory such thing happens, I would say that P brain is charged with respect to the tensor field B with a charge Q. And this is a generalization of well-known concept of charged particle. Here there is a trajectory, here is one form, we integrate. And similarly to the case of charged particle, we have a gauge transformation. B is going to be plus d lambda. So this is P plus 1 form, this is P plus 1 form, this is P form. It's a gauge transformation. And similarly to the Maxwell theory, we can write down the gauge invariant action for this B field. And this is Hodge star made out of lattice. Now, when we have a compactification, K wrapped P brain leads to a P minus 1 brain with the charge K times Q. With respect to the P4 B I1 IP B. So in this way, in brain spectroscopy, we see that P brain with the charge Q, okay, P brain leads to a tower of P minus 1 brain with tension equal RK PP and charges equal K times Q. Plus P brain unwrapped with PP and Q for B that's what happens. Any questions?
Why
Yes.
you call,
Yes?
why you call it a tower of?
Because they depend on K.
Uh,
There is something wrapped once, wrapped twice, wrapped 3 times, etc. It looks like a tower, where you have levels.
Then here, there is one small kind of thing. So charges can be both positive and negative. Like
Yes.
K takes a value in integer number. You can kind of wind in one way, wind in opposite way.
Yes.
While tension, I think from
Very
construction-
good flower. Here there is no delay.
Yeah, so indeed we will have particles of the same mass, but for the same mass there will be like 2 particles with exactly opposite charge.
Yes, of course. So would it be for particles? I can wrap strings, and they'll have particles with the opposite charges.
Excuse me, so tension just means mass? or-
That tension is coefficient. So when I'm writing an action for the P ray, it contains many terms plus, okay, it contains the main term. TP, and here is the volume of the P ray in some external method G. So simplest case that you know is particle. Particle is a zero grade. And it has the following action. It has trajectory, this is the length of trajectory, and this is called the mass of the particle. And mass of the particle is the tension of the zero gravity. Let me mention that here tension is proportional to R, to circumference. However, there is an opposite tower. So opposite tower appears like this. Suppose we have QFT, and in this QFT we have a field phi. Then we may decompose phi as phi tilde k into the I k xd over r and I take a sum over K. I am just doing Fourier expansion.
I think in this formula you also want a factor of 2 pi because you use r as the circumference, not a radius. So
Okay.
when you kind of travel by distance r in the p direction,
Yes, okay, 2 pi, yes. And then imagine that for phi I have something like so here I assume that field phi is methods. And this happens in RD. It's an integral over RD minus 1. And here I'll have phi k tilde Laplacian. Okay, Laplacian in D, Laplacian in D minus 1 dimensions plus k squared over r squared. Actually, the sign here is minus it. So here I have a sum over k not equals to 0 plus I have integral over Rd phi 0 Laplacian d minus 1 phi 0. So say for scalar particle, for scalar field, I get a tower of scalar field. Phi k is a complex field. Phi k tilde is phi k minus tilde is phi k tilde complex conjugate. As it's clear from the Fourier expansion. And I know that the mass of phi k tilde is k over r. They also form a tower, and this tower is called Kaluza tower. However, previously, branes, in particular particles, were charged with respect to something. And now it's interesting to ask if particles from the Kaluza tower are charged with respect to something. And surprisingly, the answer is yes. So first I'll make a statement, and then I'll comment. If Q of T contains gravity, then field of Kaluza tower are charged. With respect to I'll oversimplify it a bit, but with respect to the gauge field A mu, that is G mu D, where this is a metric. So what do I mean by this? I'll consider Einstein theory. On near the metric G naught. And metric G naught would be GDD G. Okay, let me put here 1, 1, 1, probably minus 1 somewhere. 0, 0, 0, 0. So it means that for G naught, a u equals to 0. Now let me try to write G. GMN. I will still keep this GDD standing here. I will have here times A U. Here I will have times G G mu D. Here G D mu, and here G mu. So the claim that I'm going to make, and you may check it, is that this component of the metric behaves as an abelian gauge field. So to behave as an abelian gauge field, we need to see something about gauge symmetry. And it was discovery of Kaluza that gauge symmetry came from the isometry of the metric G naught. Of the metric G naught. Actually, where we have a metric GMN, GMN is equivalent to GMN plus small epsilon and Lie derivative of GMN.
Yeah, but that is diffeomorphism, not isometry.
Yes, yes, it is diffeomorphism. Now, I will do the following. I will look at small changes of GMN. So change of GMN is equivalent to change of GMN plus epsilon LV G not MN. So I have small parameter here, small parameter here, and small parameter here. Now let V be isometry. Of G naught. Then I can say anything interesting. But now let me consider this very particular case. Let me take vector field Vm to be equal to Vd only this component. Okay, so Vm is 0 for m non-equal d, and Vm is lambda of x for m equals to d. Now, what can I say about such a transformation? And here I say lambda of x1 xd minus 1. So we know the transformation rules. Transformation rules say that in this particular case, we differentiate G naught. Okay. Let me write it in component. LV of G naught Mn equals V M d over dxm G naught Mn plus two other terms. G naught Mn, and here I have M tilde. And here I have derivative of M tilde over dx m plus another term like this. For this particular case, and this particular metric, the first term goes away. Here, only component where m equals to d survives. So I'm getting G not d n d lambda over d x m. And this is variation of g d I have some problem with the indices. I have m n here. And I think it's variation of g dm. So here n equals to d. And I see that variation of g dm equals up to some. You see here I have a constant factor. Equals d lambda over d x m. So if I need it, I would restore this factor. But I just wanted to show you that this off-diagonal component
Wait. G0 dn. N is less than d.
No, it should be
Those
g0 dt.
Yeah, because those components
Yes.
if n is less than d, then those components of g naught are 0.
Yes, yes, sorry. So that's why variation of g dm is like d lambda over dxm. And this is gauge transformation. So diffeomorphisms lead to gauge transformation of GDL. And this was discovery of Kaluza. The general relativity leads to gauge symmetry. And if I write action on this AM, it should be a second order action that should be invariant under the gauge transformation. So I will get a Maxwell equation, Maxwell action for A. So I promised you that my course will be very elementary. Okay, so what have we achieved? we have first massive field with mass K over R. From gravity, we have gauge field that is one form. A M A mu. That is G mu D. With the action f of A, f of A. So one may think, is it true that this massive complex fields are charged with respect to this state? And the answer would be yes. So how can I show it? How can I show it? I need to study coupling of the scalar field with the matrix of this form. So I will write field phi, and here I am writing down Laplacian. dm dd. I have this interesting thing. Okay, I will write it like this. So I have this step in R D. Because Laplacian is dm phi gm. So this is Laplacian. Okay, square root of G. And now I'm trying to extract out of this G M N GMD, G mu D. Because you may easily see that G mu D is approximately the same as A mu. Because matrix G naught is diagonal. So if you write it in this form, you put n equal to d, so you put d here. Now let us come back to our expression of phi in terms of phi tilde. So dd phi would lead to k over r phi tilde, let's say k, And here I will have du phi minus k. And here I have this a. And you may easily see here in the order linear in A. In the order linear in A. The coupling between the scalar field, charged scalar field, and the gauge.
I think we can apply du mu. No, it's du mu.
Thus, phi tilde k are charged with the charge k over R. So in this business, I was very inaccurate in treating this GDD. So actually, R would go away in this formula. But my goal is to show that Kaluza modes are charged with respect to the gauge field that is of diagonal component of the metric. It is a good exercise to do it in full detail, but I don't want to spend time on it, because there are many other interesting things that we can study here. So altogether, we have two towers. Tower proportional to R and tower that is proportional to 1 over R. And two sources of charges. One charge is coming from the tensor field, and one charge is coming from the off-diagonal component of the metric. I feel now it's a good time to make a break. So when have we started?
15 minutes ago.
15?
50.
50. Okay. Now questions.
Should it be clear why this R has to cancel? Because this G0DD, what's its relation with the compactorification radius?
You see, it is clear on dimensional graph. Charge
contains the metric and proportional to R type of, and it's like polar coordinates, and this GDD is, it can even have different units.
Yeah, I see. Yeah, it makes sense.
I have a question.
Yes.
We're doing compactification by wrapping around the cylinder. but we can consider a different figure, right? Like,
Yes. And what people are doing, they are studying compactifications or,
On Calabi-Yau.
okay, on more complicated spaces.
Like a Calabi-Yau that we have
Yes, like
all
Calabi-Yau.
over institute, like in this collection.
And Calabi-Yau that we have in front of the institute refers to the famous compactification when people started with 10-dimensional string theory, compactified it on 6-dimensional Calabi-Yau space to get the 4-dimensional theory that is close to our real world. And that is exactly a place where geometry started playing with physics, because different type of geometry correspond to different fields that we have in physics, and I will talk about it after the break, because I don't want to make break a discussion. Break is a break. During the break, I am just getting the immediate questions to be answered after the break. And of course, I will answer your question.
So that's actually like, okay, question slash comment. So when you have, when in a theory you have like many different charges, many different objects, many different charged objects of different dimensions, then at some point you need to verify some integrality conditions for charges,
Yes.
like some quantization condition. Here, like what happens to quantization conditions?
So, if charge is coming from charge before, there is a wrapping number. And in this way, we have quantization. When we compactify on a circle, we also have quantization.
No, but the story in quantization is that there should be some H bar. So usually quantization condition is that the kind of product of charges for two charged objects of some complementary directions is integer multiple of H bar.
You see, it's a good question that I'm going to explain today, after the break and in the evening session. And this is an issue of magnetic charges.
Yeah, so
Charges.
that's what I'm saying. that-
Yes, charges that I discussed right now were just electric charge. Or standard charge.
Yeah, so it's kind of hard to distinguish which ones are electric and which ones are magnetic. So I
We
think-
will come to it. At the moment, in two examples that I consider, charges are electric with respect to the form that was a B form in dimension RD in the D dimensions, and charges were electric with respect to this off-diagonal component of metric. However, of course, we are going to discuss magnetic charges too.
Okay, so there will be even more charged objects.
Yes, there will be even more charged objects. And not only charged particles, but charged brains. Okay, so now I am answering questions. So the good question was, or would be, what if we would have not just S1, what would be if we would have something more interesting? So would answer to it would be like a lecture or two. But I will say something. And here we have a space C times R n, where C is some space. And this is the action that generalizes Maxwell action to the P form. I have a Laplacian on C, and I can decompose P forms into eigenforms of delta C with eigenvalues m_k squared. And doing everything like I did, no. I will do it in another way. I will decompose dp as bl times bp minus. So this would be a L form on C. And this would be P minus L form on Rn.
What do you mean by you will decompose? Not every one can be decomposed like that. Right?
Such that Laplacian on C applied to B lambda L is what I will call m squared of lambda So it's an analog of decomposition that I have here for the scalar field. And then I plug it into such an action. And I will get the following expression. D, B, lambda, sum over lambda. Plus or minus m squared of lambda b p minus l lambda star b p minus l lambda. So for non-zero eigenvalues, I will get a massive tensor fields. However, if m square of lambda equals to 0, I will get a massless field. I will get massless. So, dimension of the space of massless P minus L forms is dimension of L cohomology of C. Here I use Hodge theory. That this is isomorphic to harmonic forms. What is the physical meaning of it? When I compactify a manifold C, its harmonic forms or its cohomology correspond to massless fields in Rn. In particular, in the world around us, we have some number of massless or nearly massless fields. If the world around us came from the higher dimensional world under compactification, we could see the topology of the space C. Now, what about gravity? And we say that G is G naught plus delta G. We plug it here, and we assume that G naught solves Einstein equation. Then the linear term in delta G vanishes, and we have some Laplacian on delta G. In metric G naught. And we need to study its spectrum. Now, why people were so excited about it? Because they studied compactification from 10 to 4. So dimension of C was 6. And people studied special compactification. Such that C is complex and scalar. And has a non-vanishing holomorphic top form. Then there was delta G ij, and there was also delta G ij bar. Delta G ij bar could be identified with H11 cohomology of C. Now what about this delta ij? It is better to write it in this way. Let me think for a moment. Probably I can write it in this. Well, let me still write it in this. This is symmetric in ij, and they are both upper limits. Now I can use G naught I bar to lower this index and use holomorphic top form JKL to lower this index. And the resulting object is omega I bar KL. And such Laplacian is identified, turns into Laplacian on 214. So massless fluctuations of matrix could be identified with cohomology of this complex space. Moreover, now I will say something, and here you should just believe me, that we have two types of massless fields. Massless fields of this type and massless fields of that type. In this model, massless fields of this type correspond to generations in quantum field theory, while massless fields of that type correspond to anti-generation. Like in standard model, we have generation. And it is known that if we have generations and anti-generations, generation together with anti-generation could get mass and become quite messy. However, generations are archival, they are all the way down until the electroweak symmetry is broken. So the number of generations in this model is H11 minus H21. And then people said, look, we know this in our real world we have 3 generations. So in this way, we can just guess compactification. Consider this complex Kähler manifolds with non-vanishing top form. They are called 3-dimensional Calabi-Yau. And look among them and try to find among them a model where this number equals 3. Then it will be compactification that describes our real world. Moreover, as you heard about, if you heard about generations, you probably heard that there are so-called Yukawa couplings, if you have generation. So Yukawa couplings had a form of product in such cohomology. If you have elements of H11, you can multiply 3 of them, and this would give you Yukawa couplings. And people were quite excited about it in the year 1984. 40 years from, was 40 years. 1984. 40 years from now. Because they got an idea that they will find proper Calabi-Yau space and understand the theory of our world. And Yukawa couplings are not something arbitrary, they are just given by multiplications on this cohomology. Actually not standard multiplication, but quantum cohomology, but nevertheless. People had an idea that they are very close to construct the unique and final model of our world. And since then, people start studying all this Calabi-Yau space. And that's why they are so famous. And they're intensively studying them for 40 years. So it is a story about compactification. Now people consider these compactifications as a part of mathematical physics, not as a part of real physics, because of some subtleties that happen. But but these spaces have many interesting phenomena. In particular, there is a mirror theory such that H11 of manifold X is H21 of manifold X check. This is called mirror. And people studied it for 35 years and still studying it. So that's what happens if you do more serious compactification. Okay? It's an answer to Maxim's question. You may ask, why this special complex manifold, why this condition of being special complex came out. Such condition kind of guarantees that you will have a solution to Einstein equation, and not only solution to Einstein equation, but special solution that preserves one supersymmetry. And you may ask, you see here we have dimension 3, complex dimension 3, real dimension 6. What happens in lower dimension? In dimension complex dimension 1, real dimension 2. The only example is a torus, not that interesting. However, in real dimension 4, that is complex dimension 2, such spaces could be classified. And there are only 2 of such spaces. One space is 4-dimensional torus, also not that interesting. But there is another space, actually unique space, with such property. And this space is called K3 space. And that's why physicists are studying these K3 spaces a lot. And I think it was Aspinwall who wrote a book on the geometry of K3 spaces. And this space is very exceptional because cohomology of this space, this K3 space, has 22-dimensional space of second cohomology. And intersection lattice on this second cohomology are quite interesting, is quite interesting. So-
Each?
Sorry?
Is that lattice
Yes, lattice,
in 22 dimensions?
yes.
Is that the famous one?
It is, so it is E8 times E8 times 3 copies of simple Lorentzian lattice. Lorentzian lattice is this one. But this is where the maximal exceptional Lie algebra E8 appears. And this space K3 plays an important role in M-theory duality, as we will see later on. So now I am saying it in advance because Maxime asked. Now, let me go to the issue of magnetic charges. So this is the action for the tensor field, P brane, and their interaction. When we have system like this, we say that we have electrically charged P brane.
And the charge should be in front of that second.
Yes. Let me do what Dirac did for electromagnetic field for the tensor field. Let me forget about brain for a moment. He said, look, this is extremal in the field C of the following action. If I take variation with respect to C, I will get dFT equals to 0. So roughly speaking, it would mean that Ft is dB T minus 1. So I can plug it here and get to original action. However, I may play an opposite game. So here I have C that is D minus P minus 1. Opposite game means that I integrate F out. And in this case, integrate F out. I will get dC D minus P minus 1 star dC D minus P minus 1.
I have a question.
Yes?
I think it's not directly related to what you're saying, but kind of tangentially maybe. So here you said that the F is 0, so F is exact, but isn't isn't the cohomology the exact thing that people play with when compactifying? So isn't this difference between these two formulations
So
important?
you see, I am doing on, okay, let me do it on RD.
Uh-huh.
Let me get the numbers. So classical electromagnetic duality corresponds to D equals 4, P equals 2, right? Then here I have 1, 4, and C is also 1 4. Now what would happen if I add here this test? I cannot write it in such a way anymore. I can write it in such a way only outside the locus of the brain. Right?
Sorry, can you repeat that again?
This b, p minus 1, could not be written in terms of f.
Oh, right.
So, I cannot run it like this. But I can try to imitate this transformation somehow. From this equation, from this action, I actually have the following equation. D star D B P minus 1 is delta form on the P brain. Or I can write it down as D star, and let me call this F. Delta function on the P brain.
FP
What?
should be FP.
FP, right. And here I have DF P equal to 0. So Dirac, many years ago, like 100 years ago, proposed to do the following: to put here delta function on magnetic brain. And you may easily check that this magnetic brain should be D minus P minus You see, this Englishman put this crazy notation, so I have always problem in getting it. So for a particle, P equals 0, and here magnetic brain It is a monopole. It's also a zero grade. So it is, I think, something like this. It is D minus P minus 4 grade. So for P equals 0, I have 0 grade. You may play with these numbers. And this is a definition of magnetic ray.
Wait. Maybe it's D minus P minus 2, because in D equals 4 and P equals 2.
Okay, P, when we speak about the brain, so here it was for P brain.
Yeah. P equals 0.
So they made the shifts in dimension. That's why formulas look unnatural.
But just to be clear, like the way to count it, in the first line, the electric line, Fp, then star is a D minus P form, then D of it is D minus P plus 1 form, so it's D minus P minus 1.
Yes.
And that's something that should be integrated against P minus
No,
1.
it's not to be integrated.
No, I mean, it should be paired with a P minus 1. So that's why we have a P brain there. Delta of a P brain, right? P minus 1.
So delta on a P brain is delta on a P brain, okay, P plus 1, is a differential form of dimension D minus P minus 1.
Should be minus P plus 1.
Yes.
So in the second line, we have a P form, then D applied, we have a P plus 1 form,
Mm-hmm.
which means on the right, we should have a P plus 1 form, but P plus 1 is D minus P plus 1.
Okay. So this is a P plus 1 form.
Yeah.
So P plus 1 form means that it is delta on something with dimension D minus P minus 1.
Yeah.
And it means the dimension of the brain is
P plus 2. Right?
so we subtract 2.
Wait. In the first line,
P brain
it's D minus,
mean minus P plus 1.
yeah. But it's D minus.
Sorry,
P
sorry,
minus
sorry,
1.
sorry. Here we have minus. Because P brain means P plus 1 dimensional world volume. And delta on P plus 1 dimensional world volume is D minus P minus 1 brain.
Well, then it doesn't match with the left hand side. Because the left hand side is clearly a D minus P plus 1. form.
Okay, well let me see. Probably here there is a star standing here. If there is a star standing here, means that the left hand side is p minus 1. Mm. So this is a p form. This is a d minus p. This is a d minus p plus 1.
Wait, why is it delta of a p brane? It shouldn't be like that, because when p equals 2, it should be delta of a 0 brane. So it should be a delta of a p minus 2 brane. And then everything matches.
Sorry, why p equals 2?
Well, in electrodynamics,
In electrodynamics,
p equals 2.
in electrodynamics, p equals 2.
And on the right-hand side,
Ah,
there is a delta of a 0 brane, because that's the world line of a particle,
yes,
charged particle.
yes.
So it should be P minus 2.
So it means that p here and p here are different.
Yeah, one should be 2 greater or 2 less than
Yes. So here, this is for D0. They call it D0 brane. And how to get 0 out of it? D minus P minus 2. No, it is delta on D minus P minus 2 brane. Okay, let's compute it again. This is a P form. When I apply star, it is D minus P form. When I apply D, it is D plus 1 minus P form. When I apply star again,
It's P minus 1, right? Maybe that, the star is, you shouldn't have added it.
so it is P minus 1 form. Right? It's P minus 1.
Yeah.
Okay. P minus 1 form means that it is delta function on something that is D minus P plus 1 dimension. Okay. Okay. So this is P minus 1 form, right?
Yeah.
It is delta on D minus P plus 1 dimensional space. Space time. And this is called
No, the dimension, wait. The dimension of the,
okay, sorry, when I take variation here, I don't have the second step. That's why it's like this. P form, D minus P, D minus P plus 1. So it is this space time, D minus P plus 1.
then it doesn't match with electrodynamics.
Well,
Or, wait, now it's,
no, so it is D minus P plus 1 form. but d minus p plus 1 form
It's the
correspond-
density, charge density.
It has to be star, now it has to be star over charge density, over current form. And if we put another star, it has to be exactly the current form. After star.
Okay, anyway, it's d minus p plus 1 form. It's d minus p plus 1 form, and d minus p plus 1 form means that it is a delta function on p minus 1 dimensional object. Dimensional object that people call delta on p minus 2 brain. Now it matches. For p equals 2, it is delta on the 0 brain that's apart. Okay. Now about magnetic. Since I raised star here, I should probably put star here. So dual equation should be like this. No? No. Right. Okay. And this is p plus 1 dimensional form, and p plus 1 dimensional form is a delta function on the d minus p minus 1 dimensional.
P prime. Okay, you need to call it some introducing P prime for object.
No, so here is p plus 1, d minus p minus 1 dimensional object that people call delta on d minus p minus 2 brain. You see, I subtract. Now it works. For p equals 2, I have 0 brain here and 0 brain here. Okay. And this is the definition of what people are calling magnetic brain. Then you may ask, is it possible to get these equations of motion from any Lagrangian? And the answer is no. You cannot write down a Lagrangian that will give you such equations. If you have simultaneously electric brain and magnetic brain. So you may try with equations like that, and you will get equations with only electric brain. Or you can replace F by star F, and you will get the equations where you have only magnetic brain. But now, let us make an assumption. Assumption says that not from the Lagrangian, but at the classical level, you may have such configuration.
What do you mean on a classical level? Just considering equations of motion?
Yes. And this is what Dirac proposed. He said you have electric charge like electron. He said maybe there is a magnetic charge. Namely, such solutions of equations of motion. And let me show you how this can happen, not in dimension 4, but in the case where d equals 2 and p equals 1. Two minus 1 minus 2. So here we will have minus 1 brain and another minus 1 brain. I told you that British people gave terrible naming.
Do you want to do it now or during the second part?
So what time is it now?
It's about 12:12.
It's thank you. I will do it in the second half.
But just to repeat my question from before, all this manipulations with replacing going from to and from B and F, this should be done more carefully when we have some more complex manifold, not
Yes,
just
of course,
RD,
of course, of
and
course.
there are some kind of maybe obstructions and some non-trivial
Yes,
elements in cohomology.
yes. But you see, first I'm trying to give you an idea. And let me just tell you what Dirac said. Dirac said that on the complement, that monopole is the following. That on the complement of the line, you have a magnetic field that looks exactly like electric field. Would this line be electrically charged? And he said this is a monopole. Okay, so we will come to this issue after the break. So now I'll give a 40-minute talk on magnetically charged objects. The first example would be very simple. I'll be with Slava Life. It is the minimal example. And the second example would be so-called Gross-Perry gravitational instanton. And the story about this Gross-Perry instanton was a paper written in 1973. In this paper, David Gross and Perry wrote that here we overcome no-go theories of someone, and Einstein. And he sent it in this way to physical letters. The referee in physical letters said, look, it's a good paper, but could you please delete that you overrun the no-go theorem by Einstein? And Gross replied, no, I insist that I overrun the no-go theory of Einstein. And he managed to publish it this way. So it is an advertisement. I will be non-technical. I will not write formulas, I will draw pictures. So people who would like to see formulas could go and see formulas. I'll try to explain what happens. Okay? And this Gross-Perry instanton plays an important role in understanding of what we know about M theory, what of M theory and what we know about M theory. Okay. So let me start with the simplest possible example. So simplest possible example is the theory dB star dB, where B is a zero form. So of course it's a minimal example. And everything would happen in dimension 2. And as you may anticipate, we will talk about -1 braces. This crazy -1 is because of crazy notational system invented by British scientists. So it's about points in space-time. So, this is the action, and how to write down something charged. To write down something charged, I will just write Q, B, at point P. And of course from this you can easily get dB equals delta of dB x equals delta equals Q delta x minus p. This equation could be easily solved. And solution is b of x is logarithm x minus p, and here I have q, and I omit factors like 2 pi. And what is dB? So f is dB. It is q dx x minus p plus dx bar x bar minus p bar. Okay, I can put one here. It's a green function for Laplacian in 2 dimensions. Okay, it's very easy to draw this on the plane. So this is the point P, and here we have arrows, and when we go far away, the value of these arrows becomes smaller because of this thing. So I would like to draw here big arrows. And here I have small arrows. But the flux of this field is the same, and it equals q. Okay? Now, let me try to imagine magnetically charged. Minus 1 volt. So I would like to replace F. I would like to say that F dual is star of F. So what does it mean to take a star? To take a star means to make a rotation. Here I have color chalk. And here I have it. Здравствуйте. Вы без четверти 4 хотели? Нет, мы специально раньше кончаем, чтобы вас слушать. Хорошо? And then we have something interesting. Integral of dB dual should be equal to Q. How this could happen? This could happen when B dual is defined moduli Q. So it means that the dual corresponds to maps to S1. So it's not just an ordinary scalar field, it's a scalar field that takes values in S1. Such configuration is called a red configuration. Is called vortex. And of course, and it's important, vortex is not defined by Q. Vortex field so actually to have this vortex configuration we should take a plane cut out a point and then draw a vortex configuration.
Well, to be fair, the original field, the electric field, was also not defined as P.
Good point. It grows while field dual is not defined. It's not just big. Let me make, it's a good point. Let me make a comment.
They both grow, and they both have different directions depending on which side you approach it from. I don't think there's a difference in this. There's a residue of one, but not of D of one, D, B, but not a residue of dual. That's a difference.
I would say the following. This situation could be regularized. If you put here epsilon regularized delta function for electric story, you can stabilize fields here. And it will still have some meaning. And then you may consider epsilon going to zero. And this is the story with electrical charges. You can smoothen them and then gradually take them to zero. In the case of magnetic charges, you cannot smoothen them. Because if you can smooth them, then you can contract. And here, it's a topology.
What's the difference if I just take the same epsilon regularized delta function on the right hand side for the equation df equal to some q delta, not d star f, but df.
Okay, so I had an impression that you cannot do it. But it's a good point to think about. that you cannot draw a configuration such that when you go this way, you will get a jump. And the side you will not get a jump. So you could not realize it as a smooth configuration.
So what if is some like vector field but with a jump? Or
So when I say jump, it means that B dual corresponds to maps to S1. And maps to S1 belong to different homotopy classes. So to see these different homotopy classes, I need to cut out this word. It's the only way how I can see it. So this is the story of vortex. And now let me briefly explain what happens in the Gross-Perry gravitational instant, if we accept it. There was such a picture, namely S1 in the fiber, and here there was a base. And this base was three-dimensional. Let me see. Yes, three-dimensional. And when you change metrically to it, you are getting electromagnetic field. And then Gross and Perry asked the following question. Could we find a magnetic monopole here? So based on the idea of cutting out a point, we would like to do something similar here, but not cutting out anything, and it's very important. What we would like to change, we would like to change the S1 vibration. So there is a bundle R4 may be considered as a S1 bundle over R3. You may ask how it could possibly be. And the answer is like this. I'll briefly mention it. That R4 is approximately S3 bundle. So we write it to this way. S3 bundle, and this is R4, over R plus. Okay? Now, S3 itself is a S1 bundle over S2. It's called Hopf fibration. So now I will say that it is S1, and here I take this S2 and put it to the base. So together I'll have S1 bundle, and here is R4, and here is S2. So I'll rearrange things in this way. So R4 is S1 bundle, so statement. R4 is S1 bundle over R3. So how can I do it? I know that R4 is S3 bundle over R plus, right? It's a radius, it's an angle. Then I pick up S1 out of this and extract S2 here and put it together with R plus. So please believe me that this construction works. Now, it is a very interesting bundle. It is a bundle with degenerating fiber. Because would it be a bundle with non-degenerating fiber, I will get that R3 times S1 equals R4. That's not true. What actually is true is the following picture. Here I have R3, and here I have this vibration, and at some moment, at some point, P, the circle shrinks to 0. But asymptotically, it goes to S1 times R3. This picture.
How does that happen? Because in the Hopf vibration, there are no like special points, right? There are no points where the fiber degenerates.
Yeah, of R plus.
On R plus.
And
Okay. Yeah, all right, that makes sense.
So I take this S3, decompose it to S1 and S2. I put S2 here to get R3. And I'm getting this, R3. And I'm getting this vibration. Or you may just believe me that it looks like this.
But isn't R plus times S2 also R3 with a removed point?
You compactify. Because when I started with S3 vibration, of course, I included the collapsing side. Okay.
Where it was
Simplest case. What is R2? R2 is S1 vibration over R plus,
where
where 0 is a special point. At this point 0, fiber collapses. However, total space R2 is pretty smooth. So it's smooth as a space, however, vibration is singular. So it can happen that vibration could be singular while the total space is smooth. With the simplest example. Slava would not. Okay. Another simple example is parabola. It's a smooth curve. It has a fiber, but at some point, 2 points collide. And this is kind of collapsing of S0. Here we have collapsing of S1. Here we have collapsing of a circle over at a point on R3. And what's interesting? It is interesting that it is possible to write solution to Einstein equation on R4 that asymptotically looks like S1 times R3 away from point P. That's why I draw it like this. So it means that far away from the point P, we have just standard Kaluza compactification and we have electrodynamics. However, at point P, the fiber collapses and the decomposition that I was writing, that G mu D is a mu, has no meaning. Decomposition has no meaning. So this metric is called Tau-Znat metric. And you may see how it looks in different books. I am not going to write down formulas. I'm trying to explain you an idea that above P, electrodynamics that comes out of gravity disappears. It's a very interesting thing. Everywhere here, in this area, you have electrodynamics that is coming by Kaluza mechanism. But here there is no electrodynamics. And in this way, situation is like here. However, this solution is smooth, solves the Einstein equation, moreover, it's hyperkähler solution. And it has finite Einstein action. And this finite Einstein action, of course, would be the coefficient in front of this solution And if I add time, then the value of the Einstein action on such solution would be the mass of Gross-Perry monopole. Wow, what a construction. And if you look at this field A mu, that is G mu D, where it exists, and if you compute magnetic field out of this field, you would see that it looks like monopole. However, at this moment, electrodynamic disappears. However, gravity is still non-singular. So when we study compactification, gravity on Sy times Sd, we do have magnetic objects. Gross-Perry. So would our world happen to be Kaluza world, we would see them around us fly with the prescribed mass. It's a pity that our world is not Kaluza world. Kaluza world is a mathematical world. But in the mathematical world of Kaluza, there are these magnetic objects. And I wanted to give you just a short talk. Yes. And we have 7 minutes for discussion of this remarkable phenomenon.
I think there are some higher analogs of vibration, something like S2 over S5 or something.
But the question is, okay, there are many things, but the question is to find a solution to Einstein equation with a finite action. Finiteness of action is important. At least I don't know anything about it.
Not finite action, finite mass.
Yes, because finite action becomes finite mass.
No, but it's kind of finite action if your time is finite. So what you want this action to be action of magnetic monopole given on a walled line. But Einstein solution is kind of for infinite time.
So Einstein.
So it's not finite action. It's actually like finite analog of gravitational. Finite certain charge in gravity. So
Yes.
They're like
Yes.
whole, literally tau-gnat charges for the
Yes.
So these are the kind of analogs of masses like in a gravity.
Yes.
But
Yes.
for this
Yes. I should say it clearer. Clearer is that if I have just this, I will have d minus 4, and now I'm thinking about this plus minus that British people added, minus 1. Great. Because when I have RD, so I take 3 dimensions out of it, and I'm taking 3 dimensions out of it, and I have S1 times R3, where I play this tau-knot metric times R d minus 3. Sorry. So it is magnetic object of the space-time extension d minus 3, and people call it d minus 4 brane. No, it's right, d minus 4. And it's a new phenomenon. You see how many interesting things could you make if you have just circle, gravity, and gauge theory. I would say gauge theory is an extra thing. Just have circle and gravity. And Kaluza completely missed it. And Dirac completely missed it. And nobody was thinking about it until Gross and Perry published their great paper in 1973. So I think that Dirac was still alive. He was looking to see his monopoles. However, his monopoles were already in Kaluza theory. Based on this nice geometry of collapsing circle. That's what I wanted to tell you. I would not say that you should study it at school, but you should definitely study it when you are studying gravity course. And since I am not giving a gravity course, I am not writing this metric in coordinates. I would say even more. You can play with the stack of such objects. It's called multi-tau-knot. You can go on and on. And if you do it like this, you will have several magnetically charged objects that are coming together. So you may put them close to each other. And here, as you see, you will have a non-contractable sphere.
So, I've just checked, there's an S3 over S4 vibration in the quaternionic vibration.
Maybe S4 over.
Oh, S4 over S3, yeah. And no, S3 over S3 is the fiber, S4 is the base.
S7.
Yeah, S7 is a vibration of S over S4 with a fiber S3. And since S3 is kind of like SU2, can we have a similar picture with a George Glashow theory, like with SU2 gauge?
Never thought about it. I have never thought
But
about it.
in like very high dimensions, 8 dimensions.
So
Just
probably,
my analogy, just doing the same thing.
you see, here there is an interesting extra thing. This metric is also solution to Einstein equation.
It is a flat metric. So that's
It's not a
that-
flat, it's a
No,
Ricci
no,
flat.
it is a flat metric because torus is as flat as plane.
But so it
if
is
you
a-
look
it is a
at
simple-
S2 times something, then it is not a solution to vacuum Einstein equation because
But-
it is not flat.
But what is important that in this case, it's not only the topology that you can write a metric.
No, so here it's also important that you don't need any sources to support this solution.
Yes.
Which might not be the case when you replace S1 to say S2 or some high dimensional sphere. Because then the whole metric will not be flat because of the curvature of a sphere. So therefore for Einstein equations you will need to support it with some charges. And that's why you will kind of violate the kind of nicest property of this metric that they are all smooth. So that's kind of differ them from Schwarzschild geometries where
And after
You
all,
have curvature equivalent.
I'm explaining introduction. So what you mentioned is having S3 there, but this would be already Klein model. So Klein in 38 replaced Kaluza model. In Kaluza model, he replaced S1 by S2 and S3. And he got Young-Mills. But to get these Young-Mills, as Slava said, you need something to support. By the way, nowadays, in string theory, we know that there is something that can support. Like
okay,
energy momentum tensor.
that's
tensor
10
field.
minutes before the next step.
Yes. So I hope I impressed you.
And tau stands for,
I don't remember. So maybe it's small tau but big nut. So, so people were writing this method.
In metric you can put only abelian group, right?
Here abelian.
Can you also put non-abelian?
To put non-abelian, you need to fight this problem with curvature.
Metric need to be sourced or something.
Yes.
Not vacuum Einstein.
yes, you do.
Yes, and so that, and we started from Kaluza plane theory and interpreted this G mu T as abelian, only
Yes,
abelian.
yes, as an
So
abelian.
we can't even put some other groups in such a
Okay, let me tell you the truth. You see, I'm trying to be as close to truth as I can. Suppose if you have multi-tau now, then you will have several abelian. However, at the same time, sometimes it happens that there are extended objects that are wrapping around these spheres. And then you will have so-called Coulomb phase of non-abelian theory. You will have some number of abelian fields here, and particles that are coming from extended objects that are wrapping these spheres would be W bosons. They would be charged with respect to these abelian groups. And in this way, you may consider this as a phase of the non-abelian gauge theory. And people study it in more advanced courses in M theory. But I am teaching you an introduction. At the same time, I'm trying to answer all questions. Yes, it is possible to make it non-abelian. And to go to the, and to restore symmetry, you just need to put all these things together. And in this way, you asymptotically restore symmetry, but in order to have this non-abelian something, you still need to have extended objects wrapping over these spheres. And it is Slava scientific advisor who explained us this picture. And he also explained us compactification of Calabi-Yau manifold.